say we've heard about dark energy and dark matter already, but what I want to do is kind of inform you of some of the evidence that we have for these unknown, these mysteries in the universe. Why do we think that they're, what's our evidence for them? Why do we think they're there? So just to give a little bit of background on me, maybe, as Michael just said, I'm a computational cosmologist. So what that means is I try and understand the theories behind how cosmology works. And what I specifically look at is, well, my interest is in galaxy formation. So to understand galaxy formation, we need to understand the structures in which galaxies form. And that means we need to understand cosmology. We need to understand the evolution of the universe. So that is where I come from. To build a simulation, where if I want to try and apply my theories, I need to come up with some kind of, I need to build on everything that's gone before and try and come up with some way of telling the simulation how the universe should evolve. So that's how we connect in with general relativity. And as Pedro said earlier, one of the things that you can do with the equations of general relativity is explain the evolution of the universe, and that's what we're trying to do in my group and in other groups around the world. So for these simulations, and so at the end I'll kind of, at the start I'm starting off with thinking about this from a simulation point of view. If we want to be able to describe what happens in the universe, if we want to build a simulation, where do we need to come from? So that's where I'll start, and then at the end I'll kind of show a little bit about where the current research is in terms of these simulations. So if we want to do a simulation, we need to have some point at which we start. Okay? It's like if you want to understand what the weather is tomorrow, if you don't know what the weather is today, there's an infinite possibility for what's going to happen tomorrow. You need to have some kind of start point where you can begin. And for that, we use, in the simulations, we're using the CMB. So Grania has already given a beautiful explanation of the CMB in our observations. So let me see if I can get this to work. So, and has shown a similar slide to this, where you begin with the Big Bang, you have some inflation, then you have the CMB where the photons can break away from the rest of the matter. And then as time evolves, you go through, you form the first stars, and you form all these galaxies, and eventually you form the Earth, and we're here and now. And you have these telescopes that can look back at the CMB and give us very precise measurements, as Grania said, of how the early universe looks. Okay, so we now have our starting point. We have this field that has these hot and cold spots, these variations in temperature which correspond to slight variations in density or how much matter is in different places. And that's where we start from. We then need to look at how we go beyond that. The slide will change. Or not. Yeah, okay. So then we need to go beyond that. We need to have an equation that brings us forward. Okay, so we start around 400,000 years after the Big Bang, and then we want to come all the way forward to 13.7 or 13.8 billion years. Okay, so that's the plan. And for this, we use Einstein's. We build on Einstein's theory of general relativity. Okay, and what these. So I obviously don't want to go into the details of the equation here, but what we want to take from this is so this is describing how the universe is expanding. And we've got some terms here that depend on the density and pressure in the universe. But then there's this added extra term here. Okay, so this is, the acceleration would be negative if we were to only have the first term. We know that the universe was not, so it's negative acceleration, these decelerations, so eventually you would expect everything to collapse. In the real universe, we know that our Milky Way is stable, it's not, the system is not collapsing. So we have this extra term here, which is called the cosmological constant, which helps us, which is basically the term that we use for dark energy. So I heard quite a nice analogy for this. So this is like if I have a pen and I throw my pen up in the air, we all expect it to fall down, right? We can work out the forces that happen and the pen falls down. What happens with dark energy is you throw the pen up in the air and the pen keeps going up. Pen accelerates upwards. And we can't explain what is causing this motion, but we can see this motion in the universe. Not with actual pens, we're kind of dominated by the gravitational force we have here. Okay, so this is where we're starting with the CMB. We have some equations of general relativity that we use. We believe that there's dark energy. The other thing that we need for these simulations to work is dark matter. So I'm now going to give a quick outline of my talk, possibly. The next button doesn't seem to like me. Okay, there we go. So the first thing that I'm going to talk about is dark energy. What evidence do we have for it? We've all been saying that all of us that have stood up here have said, and we have dark energy. And what's the, can we give, there's some examples from the CMB, but there are more examples that we should look at to try and understand where this comes from. Then I'm going to talk about dark matter. So this is the mystery matter. Dark matter implies we can't see it. If we can't see it, how do we know it's there? So I'm going to talk about some of the different forms of evidence that we have for this. Then going to pull it all back into modelling the universe, what actually happens when we include this dark energy and dark matter in our simulations. And then, so we're doing these simulations with dark energy and dark matter, but what we see when we look through a telescope is our galaxies, typically, and stars. So can we connect these theoretical models that include dark energy and dark matter, can we connect them back to what we actually observe in the real universe? Is there any connection there, or are we kind of just stabbing in the dark with this dark energy and dark matter? Okay. So I quite like
He's been depressed. All of a sudden he can't do anything.
Why are you depressed, Darby?
Tell Dr. Flicker. It's something he read.
Something you read, huh?
The universe is expanding.
The universe is expanding?
Well, the universe is everything, and if it's expanding, someday it will break apart, and that will be the end of everything.
What is that your business? He stopped doing his homework.
What's the point?
What has the universe got to do with it? You're here in Brooklyn. Brooklyn is not expanding.
It won't be expanding for billions of years, you know. And we've got to try and enjoy ourselves while we're here, huh?
So I thought this was quite a nice little segue into why we might want to answer the question of what evidence do we have for the universe is expanding. In our everyday lives, we obviously don't experience this. So how should we think about this? This is just another clip. So if you think about this as raisin bread, so you use some dough, you add some raisins, the raisins are kind of distributed throughout it. As that bread expands, the little raisins in the universe, or well, in our bread universe, they're going to move apart. The raisins themselves are not going to be torn to shreds, but the raisins are going to move apart. Okay? So the space between the raisins is expanding due to the dough. And we can think about our expanding universe in a similar way. Another example that's often used is if you have a number of ants on a balloon, you blow into that balloon, each of the ants will move further away from all of the other ants on the balloon. It's not that all of the ants are moving away from a given ant, but if you go to each of the ants, they all see the same thing. It's not like we live in a particular part of the universe where we happen to see everything moving away from us. So then, if we have this expansion, then what we expect, as with the ants in the balloon, with the raisins in the dough, is that we should observe the other galaxies in the universe moving away from us. Okay? So if we want to think about galaxies moving away from us, first off, if we want to measure this, first off we need to know how far away them galaxies are. And the second thing we need to know is how fast are them galaxies moving. So there's been some nice ways of measuring this, and one of the ways is using type 1a supernova. Okay, so when a star comes to, well, in the case of type 1a supernova, a star can accrete matter from a neighbouring massive star, and then eventually it becomes unstable and goes bang. Okay, and this creates a very, very bright burst of light. But there's some evidence for the fact that these types of supernova are all consistent. So if you have one going off in one part of the universe and one going off in another part of the universe, they should emit the same light. But then if you think about, so that means that if you have the same light bulb, so let's say you have a light bulb or even a candle and you have it, I hold it at arm's length, and then someone else holds one two arms length away from me, someone else holds one at the back of the room. The difference in the light that I see, the luminosity of that light that's coming towards me, it decreases as you go further and further away. So you can tell relative distance using this method quite accurately. Okay? So this gives us some impression of how far away a galaxy is. We look for galaxies that have these supernova events, and then we can tell how far away that galaxy is than the one over here, just by looking at the relative luminosity of these lights. So we now have some distance measurements, so we can put some points on our plot, but only along one axis. So we need to measure velocity. So this uses redshift, which Haranya has already introduced as a concept. So as space expands, the wavelengths of light become the wavelengths of light are stretched. So you end up with light moving to lower frequencies as it moves away from, or as a galaxy is moving away from the light emitted from that galaxy. So another way to think about this is the Doppler shift, which some of you may have come across. So when you have, let's say, a siren, and that's moving towards you, it increases the frequency, and as it's moving away from you, it decreases the frequency. So we're only looking here at galaxies. The galaxies are all moving away from us in this expanding universe. So their frequency is lower as a result of this redshift. Okay, so we can use this redshift. We can measure how much the light has been stretched between the time that it's emitted in one galaxy and we observe it. And just to give an idea of how that works. So when we look at light, we see many different wavelengths, the wavelengths coming from the galaxies. But we can see these individual features, right? And these features correspond to the excitation of atoms. So for example, if you have a hydrogen atom, and there's an electron orbiting the nucleus, if that's excited, it can move into a higher energy state, and then when that de-excites, then you get an emission line, a photon of a particular wavelength is emitted, and that corresponds to these spikes that you see in this, which is called a spectrum. So it's just the amount of light per unit wavelength. And what happens when you move? So this moves at redshift, what we call redshift 0. So that would be like if the galaxy was right beside it. This moves at redshift 0.1. So this was moving away from us, and you see that this feature moves to a longer wavelength. Okay, so that's the signature that we're looking for when we're looking at these galaxies, trying to understand what speed they're moving at, and we can relate that stretch in wavelength then back to a change in velocity. And then what we end up with, after we've converted our redshift into a velocity, we have distance and velocity, and you see that as you go further away, the velocity increases, which was what we expected from our expanding universe. Recently, there's been extremely precise measurements made of this, and we in fact find that the universe, the velocities of these galaxies is slightly higher than what we expect. Or the velocity as you go further away gets slightly higher. So that corresponds to the fact that the universe is accelerating. This is our dark energy, right, causing this acceleration. And this resulted in the 2011 Nobel Prize for Physics. So these very, very precise measurements are now giving us confirmation of this idea that the universe is expanding and accelerating, and has resulted in a Nobel Prize. So that's some cool evidence for the expanding universe. So another example, and this builds quite nicely actually onto one of the topics that Haranya was talking about. So in the early universe, as has been explained, the photons and baryons, what I mean by baryons is just ordinary matter, atoms, electrons, neutrons, this kind of stuff, they're all just a big mess. They're all just hanging out, kind of floating around each other in a hot fluid. Okay? And the difference between, or the gravitational force and the pressure from these photons resulted in these sound waves, which we heard a sound clip of earlier, where we could hear these slight vibrations. And those sound waves then, when the photons and the ordinary matter separated, when the photons could then travel freely through the universe, what happened was the waves, the peaks of the waves, corresponded to a certain scale. And at them peaks, just like if you drop a pebble in some water and you see the wave form, you see that at some point there's a peak, and at that peak the water is more compressed. Okay? So we have the same thing in the early universe. The baryons, the ordinary matter, is more compressed at these points. Okay? So they produce this very nice plot here, which we saw earlier. Okay? So, maybe not go back. So what we have then is this scale, basically this ruler in the early universe. We know at what, we can understand from the CMB observations what scale these waves correspond to, and when they froze in time when the photons could escape. So we can now, today, we'd expect that those waves that we saw, those high density regions, would contain more galaxies than on average, because of the fact that there was this compression. So then we can measure that today using, so the first measurement of this was in 2005 using SDSS, which is the Sloan Digital Skies survey, which is a galaxy survey. So it's looking at it's a really, really large survey that looks at, it's like a few million galaxies that they look at, and they try and understand